All right, welcome to our video on population ecology. So this is really looking at the first level of ecology because it's looking at probably the most specific thing where you're looking at one species and how that species interacts with other members of those individuals in the species. It focuses on things like birth and death rates. It focuses on things like how individuals in a population are distributed. What it doesn't really focus on is things that are related to behavioral ecology, things like mating behaviors and stuff like that. So mostly what we're going to look at is we're going to look at birth and death rates and how populations are distributed. So before we get into that, we have to be able to define what a population actually is, and it's very similar to the definition of what a species is. It's a group of individuals that live in an area that can potentially interbreed and produce viable, fertile offspring. So it's one species. Remember, that's what population ecology deals with. So the first thing we want to kind of get into is the difference between population density and population dispersion. So population density really just looks at the number of the individuals per unit area, or volume, but usually per unit area when we're talking about an actual population. Think about what density means in earth science or chemistry or physics, right? Density is the amount of matter within a given unit volume. The more matter there is within that space, the more dense it will be. The same thing's true about a population. Think about where there is most dense populations in terms of human beings. They tend to be around cities and things like that. In rural areas, you have less population density. So all density is the number of individuals per unit area, whatever that unit area ends up being. Dispersion is the pattern in which those individuals are distributed, how they're spaced out. Are they clumped together? Are they evenly distributed or evenly spaced throughout? Or is it just a random distribution or dispersion of individuals? Before we get into the dispersion stuff, I want to talk a little bit about how do we as scientists actually experimentally determine population size. So if we're trying to figure out the number of individuals that exist in a given area, how do we do that? It's actually, if you were to ask that question at the beginning of the year, or if I were to ask you that question at the beginning of the year, a lot of people would say, well, the most accurate way to do it would be to count every individual. That is not feasible whatsoever. So we use a sampling technique called the mark and recapture method, where we can actually estimate population size by capturing a number of individuals and marking them, which would be the total number marked right here. And we're trying to figure out n. This is what we're going to solve for. What you then do is you release them back, and you come back later, give them time to redistribute themselves, and you actually measure when you take that same, when you do another sample size, you count the number of recaptures of the original marked individuals that you had. And when you do that, you set up a proportion, solve for n, and you can actually determine your estimated population size based on that. This is not something you have to memorize. They have in the past given you this and explained the whole thing to you, and you had to solve for n. So you just never know what they're going to put on there sometimes. But if it's other than all of the math that we've specifically talked about, and I said will be on it, or math that's found on your reference table, most of it will be explained to you if it's on there. Okay, so let's get into dispersion or distribution. So there's three types of dispersion that exist: clumped, uniform, or even dispersion, and random dispersion. And there's different environmental and social factors within that population that will influence the spacing of individuals. So a clumped dispersion is the first one we'll focus on, and that's where individuals will aggregate into groups. Okay, so this is influenced on things like resources. If resources are clumped, we'll tend to want to be around certain individuals. If resources are more evenly distributed, maybe they'll be more evenly distributed. So really this is influenced on resource availability, but it's also influenced on social interactions. Things like schools of fish, as you can see here, or individuals that travel in packs. Those would be clumped dispersion. And the purpose of that, what's the evolutionary benefit for that, is their strength in numbers. Uniform dispersion, on the other hand, is when we have evenly distributed resources. Now that's a little bit more rare, but we also have, no, thank you, I'm good. What we also have is Social interactions like territoriality, where individuals have their own territory and there's borders to that territory, and individuals will evenly distribute themselves within a given space based on those borders. So that's why you'd have a uniform distribution. Random distribution or dispersion can be just due to randomness. So that's not really, that's kind of our default, right? If they're randomly distributed. So I'm not going to worry about that one too much. Okay, the next thing that population ecology tends to focus on is demography, which is the study of the vital statistics, or the living and dying that's going on in a population over time. And death rates and birth rates tend to be the thing that we focus on when we're looking at demography. So I show you 3 different types of curves here. They all look different. And I want you to look at each one and try to tell me some information about each. So we have this one with trees, okay? This is how old the trees are, and this is the number of survivors, okay? And here we have several different species of, I think it's either birds or rodents. I'm not sure specifically, or it could be ducks, actually. What is this type of graph showing? Now, they all have age, and they all have number of individuals on the y-axis. But each is showing us something different. Here, again, we have that. We look, and we have a curve that looks like this. So it's almost like the opposite of this one. So we have 3 different ones. This one, this is the opposite of this one, and then this one, which is kind of an intermediate between the 2. So I want you to think for a second and come up with a reason or why each of these would look the way that they do. Remember, this has to do with survivorship. And how long do they survive? Okay. So what these are called, they're called survivorship curves. And we create survivorship curves usually from survivorship tables or life tables. And basically, life tables look at how many individuals are within certain age groupings. How many does it start off with? How many do we have by the time we get to 80 and over? And as well as the number of, it'll tell you the number of deaths that are here. And then it gives you a probability of death within that given grouping. Now notice the probability of death, so that this is a human life table. The probability of death initially is a little bit higher early on, probably due to infant mortality. Then between 1 and 5, it drops substantially. Between 5 and 10, it drops again, and it drops, and then it slowly increases again. Interestingly enough, between 35 and 40 has the lowest. And then what you have is you have an increase steadily, except between 60 and 65 in this particular population. But then when you get to 80 and over, and 75 and 80, you have a much higher rate of death during those periods. And that kind of makes sense. And this shows you a survivorship curve of males and females, both before 1950, which is these 2 curves right here, and after 1950, which is these 2 curves right here. The first thing you want to notice is females always live longer than males, regardless of if you're more before 1950 or after 1950. It's a little bit more drastic after 1950. Another thing you want to notice, differences between before and after 1950. 1950 has a sharp drop in infant mortality early on, right? There's a big drop in children. We don't see that anymore, and that's likely due to advances in science and medicine. And this is a little bit more steady deaths over time. And here we tend to have very low mortality now until we reach about 65, and then it starts to increase. And then by the time you get to 100, you have almost no individuals left. So this is all information you can get from survivorship curves. Let's think, why would males and females have differences in survivorship? So there's lots of different hypotheses, but one would be that traditionally, now this is not the case anymore as much, but males tend to be in more tended to be in more hazardous work environments. So especially in the 1960s, 70s, and even the 80s, males tend to do more labor jobs where they were in working conditions that probably were suboptimal. It was stressful, it was exhausting, and that could have limited their survivorship. But males also tend to have more heart disease and things like that. So, okay, so these different types of survivorship curves, the ones that we looked at previously, have names. They're called type 1, type 2, and type 3. Type 1 is the one that human beings show, where we have very low survivorship. We have very high survivorship early on, and it's not until much later in life that we have a significant drop-off in individuals once they get old enough to where they'll die. And a type 3 curve is the opposite of that. In a type 3 curve, what you have is massive death early on, but if you do survive, you're going to tend to live a long life. Okay, so that's a type 3 curve. A type 2 curve is where it's pretty steady throughout your life. Now, type 1 is indicative of things like human beings or more social animals where they have lots of parental care. They only have a few children, and they really take care of those children and hope they survive to adulthood. A type 3 individual is where a lot of the parental energy is spent on actually producing tons of offspring, thousands and thousands of them in some instances, and what happens is almost all of them die, but they hope that only a few survive, but there's no parental care in those individuals. In a type 2, it's kind of an intermediate between that. You have kind of, as I said, an equal level of death throughout the entire, throughout the lifespans of individuals. So as I said, type 1, characterized by not many offspring, parental care, high survivorship into adulthood. Type 2, characterized by intermediate amounts of offspring, steady death rates throughout adulthood and childhood. Rodents and birds would be examples of those. And then type 3, characterized by tons of offspring but very low survivorship. A good example of that would be things like sea turtles, where they produce tons. The mother doesn't take care of them. There's this mad rush to the ocean, and they get picked off by birds. Only a few survive. And then this is disgusting, but it's showing a praying mantis egg sac, and all of the praying mantises that are released, thousands of them, the mother doesn't take care of any of them. They kind of eat each other too, and only the strongest ones survive. Fish also show this type of survivorship as well. All right, so what are the things that can affect population size? Well, there's density-dependent factors and density-independent factors. I'm going to go into density-independent factors first, actually. So a density-independent factor would be a factor that, regardless of how many individuals there are, it can still have a major impact on limiting the population. Things like weather and climate can limit that. It doesn't matter how many individuals there are, then you'll still have, it'll kind of be an equal amount of death. Periodic disturbances like major, like earthquakes, tsunamis, major disasters. It doesn't matter how many individuals are there. If it's hit by a hurricane, it's likely a lot of those individuals will die. And it doesn't matter how dense the population is. The density-dependent factor gets worse with population density, or as population density increases. So competition gets stronger the more that individuals there are in the population in a given area. Predation increases because there's more individuals that predators can actually attack. Stress or overcrowding, that makes sense. But waste accumulation as well, and disease spreading. The more dense a population is, the more that you accumulate waste, and the more easily disease can spread within that population. All right, so this is a very important thing to understand. There's two main types of species, the way we classify them based on their styles of living, I should say. So there's K-selected and R-selected species. And we're going to talk about what K actually means in a little bit. But a K-selected organism are great survivors. They are good at competing for resources. They are sensitive to density-dependent factors. And most are large organisms. They're usually found in environments that are relatively stable. Doesn't mean that they can't be in not stable environments, but usually these thrive in stable, very complex communities. Our selected species, on the other hand, are organisms that reproduce like crazy. They have lots of offspring. They hope some survive. Most are very small organisms. If they're mammals, they're rodents. And they tend to live in environments that are not stable, places that are not as complex, or communities are not as complex. So the way I like to think of our selected species is they are live fast, die young species. All right, so let's look at each one. What do you think? Bacteria, R or K selected? Bacteria are selected. Lots of individuals, only a few survive. They reproduce asexually, they reproduce quickly. How about dandelions? Dandelions are also selected. They're all over the place. They thrive in places like lawns that are kind of not very complex communities. How about an elephant? That is K-selected. There's not very many of them. They're very large. They thrive in more complex areas. Same thing with humans. They are also K-selected. Large trees, K-selected. How about these rodents? Rodents are more R-selected. Okay, they can, it doesn't mean that they can't live in stable environments, they can, but they tend to be more dominant within unstable environments. Another piece of information, or another way we kind of classify organisms, is based on their reproductive styling. So individuals that are semiparous or exhibit semiparity are ones that do Big Bang reproduction. That means they reproduce once in their lives and they die right afterwards. The Pacific salmon is a great example, which is this individual right up here, or these individuals right up here. They are born in streams. They then swim out to the ocean. They live most of their adult life in the ocean. And then when they're ready to reproduce, they go and swim back upstream. And this is a very taxing process. It takes them a really long time. It uses all their energy. And as soon as they get to where they want to spawn or lay their eggs and sperm, they will do so. And they'll all dump out their eggs and sperm at once into the water. And then they all die. And this is actually a very important part of ecosystems, even the terrestrial ecosystems that exist around those streams, because the bears will take their carcasses, they'll bring them out, and then the bears will eat will have an ample food source, but then they leave the carcasses there, which influx nitrogen and nutrients into the environment. So this is actually a very important thing that happens, but they only reproduce once, and then they die. Heteroparity, on the other hand, is what we do, or a lot of other things. We have, like bunnies here. You can reproduce multiple times, multiple different seasons, over and over and over again. So this is usually what you think of as most organisms being able to do. If I go back to semiparity, though, things like insects will do this. Like if you've ever seen Charlotte's Web, spiders do that. They reproduce once and they die. They only live for that one season. Okay, so this part gets a little bit more difficult. And it's not even that difficult, but it involves a little bit of math. So if we're looking at population size and increases in population size, or per capita rates of increase, we're going to look at a couple of different factors, but it focuses mostly on birth rates and death rates. If we ignore immigration and emigration, which you could take into account, but we're not going to take that into account, a population's growth rate will equal the number of births minus the number of deaths, right? That does not take into account per capita, and I'll explain that in a minute. So if you take the number of births minus the number of deaths, if it's a positive number, that means the population is increasing by that number of individuals. And if it's a negative number, that means the population is decreasing by that number of individuals. More births, increasing. More deaths than births, decreasing. Per capita, though, has to take into account the initial population size. And you're going to see why this is important in a second. So it's B minus D divided by N. And N, in this case, is the number of individuals entering that generation. You can also calculate the birth rate and the death rate by taking the big B, the number of births, and dividing it by N, and then subtracting it from the big D divided by the number of individuals initially to get those rates. Or you can just do it individually, B minus D over N. And that would give you your per capita rate of growth. So here's an example. So a population of owls starts at 1,000 individuals. Over the course of the year, 50 were born and 30 died. What is the rate of increase and per capita rate of increase of the population? So the rate of increase is just births minus deaths. So that's 20 individuals gained. But if we want to figure out the per capita rate of increase, we take the 20 individuals and divide by the initial 1,000 that went in. And that shows a birth rate of 0.02. Okay? Which is the same as saying, per those 1,000 individuals, 20 individuals will be gained within that year. But if we want to look at population growth over time, this is kind of where that per capita rate comes in. So if you take into account that steady per capita growth rate, and there's no factors that are going to limit population growth, which has not really happened, and the population will show what's called exponential growth, or a J-shaped curve, where the population just keeps increasing and increasing and increasing over time. The exponential growth equation, which is on your AP reference table, is dn dt, which is the change in number of individuals over the change in time, is equal to R max, which is your per capita rate of growth, which we calculated before, times the number of individuals entering that population, or entering from that population, entering that generation. So we're going to do an example. We're going to look again at that the owl example in a second. But so exponential growth would look like this. You see, it's a J-shaped curve. This is idealized, though. Remember, it probably doesn't happen. Why? Think about it. I want you to come up with a reason why you may think that happened. That would happen. It's because of limiting resources. There's not enough resources for them possibly to survive, for all of them to survive, and for it to continue to grow like that. Think what Malthus said. Remember, there's a struggle for existence because there's limited resources, and that humans, their population could never possibly, or eventually it's going to hit this this point in which we can no longer survive because we have too many, we're using too many resources. Okay, when we actually do the calculation, as you'll see in a second, to get the next generation, so you do one generation, then you do the second one. When you plug into the equation your output, the answer is just the number of individuals you increase by. So if you want to know the number of individuals that are entering the next generation, you have to add it to our original number, or subtract it, depending on if it's a positive or negative growth rate. It's almost always positive. If you do the next generation then, to figure out generation 2 going into generation 3, you then take the same growth rate that you had and you plug in the new n that you had. And you continue doing that process over and over again for every single generation. But you continuously use the same R max. And you can see the differences in each R max here. So this is a growth rate of 1. That would be basically a population doubling every single year. And this is a growth rate of 0.5. It's not quite doubling. It's probably increasing by about a quarter every year. All right, so let's try a problem. Back to the owls again. Population of owls starts out at 1,000 individuals. Over the course of the year, 150 were born and 50 died. What will the population size be after 3 generations if per capita growth rate remains steady? All right, so how do you figure out your R max? Well, the way you calculate the R max, again, remember, is to take the number of individuals that were born and subtract from them a number of individuals that were died. That gives you 100 as our growth rate. To get the per capita, we take 100 and divide by the initial population size, which was 1,000. And that's why we get an R max of 0.1. We then plug it into an exponential growth equation. dn dt equals R max, or 0.1, times n, which is the initial population size of 1,000, and that gives us our 100 individuals. We then take that and add it to our initial population size, and that is our new population size at the beginning of generation 2, which in this case is 1,100. Then we do the second generation. Our R max stays the same. It does not change. We then plug it in, but now we multiply it by that population, 1,100. That goes into generation 2. How many individuals are now being born? Or how much is that population increasing by now? 110 individuals. We then add that back to the original, which is 1,100, giving us a total of 1,210. So for generation 3, after generation 3, R max stays the same. Multiply R max by 1,210, you get 121. The new population at the beginning of generation 4, or the end of generation 3, in this case, is now 1,331. Okay, which, as you can see, as the population grows, you increase the number of individuals. But exponential growth cannot be sustained for a really long time in any population. That's because there's limiting factors. Resources are limited, space is limited. This causes an increase in competition. So we actually have a mathematical model that can take this into account. It's called the logistic model, and it introduces a concept called carrying capacity. You probably learned about this freshman year, but carrying capacity, or K, is the maximum number of individuals a population can possibly support. Now, what the the mathematical equation consists of is the same thing as the exponential, r max times n, but we add the carrying capacity component, which is k minus n over k. So what happens in this is that as n approaches k, or the number of individuals approach the carrying capacity, which is the total number of individuals that that particular environment can hold, as n approaches k, the growth rate is reduced by that factor of k minus n over k. So for example, if the initial population size is 1, that's, let's say, so in this case it's 1,500, right? That's the carrying capacity. So you plug 1,500 minus 1 over 1,500. We're barely reducing it at all. It's going to be 1,499 divided by 1,500, which is essentially 1. So it grows very similar to exponential growth early on. But as n approaches k, so as n approaches 1,500, so if let's say n is the opposite now, 1,499, almost 1,500. Well, 1,500 minus 1,499 is 1 over 1,500. So reducing the R max by 1/1500th of what it originally was, which is basically 0. And that's why the curve will start to level off as n approaches k. This is kind of similar to a limit when you're learning about limits in calculus and stuff like that. So you have your greatest rate early on, and as n approaches k, rate diminishes. So some populations can maintain the carrying capacity. They go up and they increase and they kind of steadily stay right around it. You could be asked to graphically interpret where the carrying, or what the value of carrying capacity could be approximately on the AP Bio exam as a grid-in or a multiple choice question. Some populations will overshoot the K, as you can see here with the Daphnia. It overshoots it, it uses lots of resources, and then it'll crash a little bit, and then eventually it'll settle down at K. And then other individual species have these boom and bust types of growth, where you go really high and overshoot K, and then drop below, and then overshoot and drop below. So you can see here, estimate the population or carrying capacity here. I want you to type it in. It should be about 900. Estimate this one. It should be about, type it in, like 135 approximately, give or take. And how about this last one? Estimate it. This one's a little bit harder. Pick something in the middle. Let's say maybe 35-ish to 40. Okay? Okay, now we're going to have the same owls, but now we're going to add a carrying capacity. Same individuals. We're going to keep an R max of 0.1. 1,000 individuals to start. So our R max is 0.1. We multiply it by 1,000. But now we have to add the carrying capacity component, the k minus n over k. So in this case, the carrying capacity, as it says, is 2,200 individuals. We're going to do the same 3 generations. We start with, so you take 2,200 minus 1,000 divided by 2,200, and notice you get 54.5 individuals. If we go back to the other one, how many individuals did it increase by? It increased by 100 last time. Now it only increased by 54.5, and that's because of this k minus n over k component. Now we take that number, we plug that in as our n. Now it's even a little bit higher. Now we add by 54.9 or 55 individuals. The new populations now remember, you can't have a 0.9 of an individual, but we're going to keep them as decimals for now. You have 1,108.9 individuals at the end of the second generation, or the beginning of the third. And then we do the third generation, we end up with 55 individuals are added to it. And now we end up with, at the end of 3 generations, 1,164. Compare that to the 1,331 if it's exponential. So you can see how the carrying capacity component has lowered the rate because of limited resources. Now, I mentioned to you guys that nothing really grows exponentially in nature. So the human population growth curve is an anomaly. Now, why are we able to do that? Now, if you look at human beings, we've been around for a really long time, estimates around 200,000 years approximately, based on evidence that we've collected and fossil bones and fossil evidence that we found. But you can see here, from 8,000 BC all the way until just right around, let's say, the Middle Ages, and even into almost the 1600s, the population didn't grow by very much. It was pretty low. It was all way under 1 billion. It's not until this point, right around here, when the population started to skyrocket. So the first thing I want you to notice is the plague. Now, the plague looks like a blip on this curve right here, but it's not a blip. A third of people died during the plague, which is an insane number worldwide. But what caused this increase right here, from here to present day, and we're even up above 7 billion now? It was the creation of science, the Enlightenment, that did that. So human population increased steadily until about 1650 and then began to grow exponentially. And that's because, as I said, of the scientific revolution and the Enlightenment, and because of the invention of medicine and technology. That now leads us to this question: what is our carrying capacity? That's a tough question to really answer, because we've had them in the past, but because of our intelligence as a species, we are able to manipulate our environment, manipulate the world, to allow us to go beyond a carrying capacity, to continue to grow exponentially. Now, at some point, we're going to have to kind of level that off. There's only a certain number of individuals that the Earth probably can actually hold. But it's because of technology, because of medicine, because of science, that we have been able to exponentially grow so substantially. All right, so this actually relates a little bit more to community ecology, but because it's looking at interactions between two different species. But you can see how, like, a lot of predator-prey relationships exhibit boom or bust population increases and decreases, where the predator, if the prey increases, the predator will then increase because it is a food source, but that'll cause the prey to decrease, which then causes the predator to decrease, so they won't have enough food. So this is called the predator-prey oscillation. One of the things that they have you do occasionally is look at the lag time from one to the other, a max to a max or a min to a min. And basically, you would subtract the min from the min and figure out, like, how long does it take for one to lag, the predator to lag behind the prey. So this is actually a very common thing that they show almost every single year on the AP exam. So just be aware and be able to interpret this. The last thing we're going to talk about in population ecology are age structure diagrams, which basically looks at kind of the percentage of individuals within small demographic groups based on their ages within a population. So it tells you the number of individuals who are that are males and females between like 0 and 5 years old, between 6 and 10 years old, or something like that. And it shows you a lot of interesting different things that you can actually look at. So one of them is it can predict population growth trends. Another thing it can actually do is it actually illuminates social conditions within that population. And because of that, it can actually help you plan for the future. So let's look at a few of them real quick. If you look at the one all the way on the very left, that's showing Kenya's population growth. And what this is indicative of is an explosion, like exponential growth, essentially. You can see here there's the highest percentage of individuals are very young, mostly teenagers, and very low percentage of individuals, or a very low percentage of individuals, are actually older, especially when you compare it to the United States and Italy. Okay, now why is that? First off, Kenya is a third world country. They have very high birth rates because they're mostly agricultural. And as a result, having more children in Kenya is actually a benefit to a family, especially if they own a farm. That means more workers, more people to help feed the rest of the family if your family owns a farm, or more people to work to support the family in general. Another issue there is they have very little sex education and lower education in general, so they don't really understand birth control methods as much. So you can tend to have population growth rates that are very high. So in Kenya, more children means more money. In the United States, it's a little bit different, and you notice there's a lot of different things we're going to look at here in a second, but you don't have that great growth. You have very slow growth here, which is a stable growing trend. And in the United States, having more children means less money because you have to feed them, you have to put them through college. So supporting them is expensive. So as a country becomes more and more first world, you tend to see birth rates drop substantially because of that reason. Another thing that you see in here is the United States has this bump out here. That's a result of the baby boom after the Second World War. And obviously that's why so many people they tell people to go into healthcare now and into the future, because these baby boomers are now moving into their 60s and 70s, and some even their 80s, and they are going to need a lot of health care as they get older. but also issues with supporting them with things like Social Security and stuff like that. So all of these are issues that the United States are going to have to deal with. And you can see that this age structure diagram illuminates that. Italy has an even bigger problem. You can actually see they're decreasing in size here. There's so few people being born, and they're going to have a very difficult time supporting the elderly as time goes on. So you have a rapid growth model in Kenya, like a third world country. You have the United States as a first world country that has a slow growth or a steady growth model. And then you have a zero growth or decrease model, as you can see in Italy. All right, that is population ecology.